The introduction, and thanks very much to the organizers for the invitation to speak. It's a pleasure to be here. My first trip to Cambridge, hopefully not my last, and and a great conference to be attending. So I'm very happy to be here. So I'd like to talk about the following. I'd like to talk about manifolds. So I'm really going to talk about a category of manifolds. Manifolds with boundary, which I'll denote manifold, so abbreviated, of a fixed dimension n. And I'll put this symbol d here to mean I'm going to allow them to have boundary, although they don't have to have boundary. So this category that I'm going to talk about has objects equal to n manifolds, possibly with boundary, and not necessarily compact. So I'm allowing, let's say, like a half-open collar or something like that as a perfectly fine object. And we're at the with maps, with morphisms equal to embeddings that preserve the boundary. So this is the thing I'd like to study. If you're one of the people who is looking for a technical error, I've made two. The first error I made is that really I'm going to restrict to manifolds that are not too big. I'm going to exclude, let's say, surfaces of infinite genus. So if that's one of the things you were hoping to hear about, there's a formal way of including it, but for simplicity, I'll exclude it. And then when I mean with boundary, I would also like them to have a trivialization of a tubular neighborhood of the boundary, and my embedding should preserve that trivialization. So I'm going to exclude those details from the talk for, to kind of keep the story flowing. But if you want to sit there and be angry at me for having taken them out, then I'm sorry. Okay, so I'd like to understand manifolds. That's how I am, and so. The way I'd like to approach that question is I'd really like to understand functors out of this category. So something that associates like a chain complex or a spectrum or a space in some natural way to every n manifold, and functor with respect to embeddings. That's what I'd like to do here. So, but before we go on, it's sort of helpful just to note like what kind of structure we see here, because it's interesting even in the most trivial cases. So let's work out an example of what this category of manifolds with boundary looks like, let's say in the case n equals 1. So here we're looking at one manifolds with boundary, and there are not that many examples here. So these things are all finite disjoint unions of things which are isomorphic to, let's say, R. Well, that's a good example. Then there's maybe the closed interval, -1, 1. And then something like a half-open interval, -1, but then excluding the point 1. Right? And I guess there's the circle, too. Yeah. And I think that's all of them. So everything is a finite disjoint union, and so there are lots of embeddings. For instance, they're interested in embeddings of R into the closed interval, mapping into the interior. There are interesting embeddings of the half-open interval into the closed interval. There are also interesting embeddings of R into the half-open interval, and there are interesting embeddings of, say, R into S1, but there are no embeddings in the way I've set it up, of either of these intervals into S1. Neither of these embed into S1 or into R, because boundary has to go to boundary, and both of those manifolds have empty boundary, and there's no map from the non-empty set to the empty set, the way I'm setting it up here. Okay, so this is how it looks with n equals 1, but now some of these objects are very different than other of these objects. So for instance, if you think about the way R looks in this category, there are lots of embeddings from R disjoint R into R. There are lots of them. And in fact, these embeddings, these are up to homotopy. And in this case, that means isotopy. So up to isotopy of embeddings. This makes R an associative algebra in this category of one manifolds with boundary with respect to disjoint union. So this observation, I think, is one of the key points in maybe the history of topological operads, that R is an algebra with respect to disjoint union in the category of manifolds with embeddings. That's sort of where I think a lot of things went from there. And in particular, so the next, if you're bored and you haven't seen it before, the next thing to work out is then that something like the half open interval minus 1, 1 is an R module. Again, up to sort of coherent systems of isotopies, in that there's a natural, there are lots of choices of embeddings of, let's say, R disjoint union, the half open interval, into the half open interval. And that's by squeezing the half open interval into itself by the open end, retracting it in, and then just plugging a copy of R into the piece that you missed. Now that's not really associative on the nose, but you can take care of that and just, in fact, take this maybe as your definition of what an associative algebra and a left module for it could be if you're going to work in a homotopy theoretic setting. Okay, so this is a little bit how things work when n equals 1. And it's good to bear in mind because these observations that this is an algebra and this is a module are going to be used on this board now. So my big object of interest here are not just functors out of this category of manifolds. It's functors out of this category of manifolds that, in some sense, for which the global values are determined by the local values. I'm interested in things that are like homology theories. So I'll make the following definition. A factorization homology theory for n manifolds with boundary and valued. Well, I've got to choose where it's valued, so I'm going to choose that it can be valued basically anywhere, C. C is some category where it makes sense for homology theories to be valued, let's say, and C has a symmetric monoidal structure, is a symmetric monoidal functor let's say F from this collection of n manifolds with boundary to C, sending disjoint union to whatever monoidal structure it was, in other words, the value of a collection of manifolds M sub I is going to be equivalent to, I'll write it as the tensor symbol, since that's standard for general symmetric monoidal structures which have not been specified, but it could be anything, almost anything, of the individual values, and such that it satisfies one additional condition. So such that any time you have a gluing of a manifold M along a codimension 1 submanifold, we write it this way, M0 times R, M plus 1. So if I choose some way of expressing a manifold M as cut along a codimension 1 submanifold, which I've written M0 here, times a trivialized tubular neighborhood, that you should be able to calculate the value of F on M in terms of these three other values. Then F of M is naturally equivalent in C to the value Fm minus 1 tensored, whatever tensor means in C, the value f0 times r with the value f of m plus 1. Well, it's very convenient that you asked. So why does this, we just have 4 random symbols here, and in general it doesn't make sense to just take something and put it underneath a tensor symbol. However, I conveniently worked out this example ahead of time, and we noted that R was an algebra in manifolds with disjoint union, and that F is a symmetric monoidal functor. So since R is an algebra in manifolds with disjoint union, when I take a product, M0 times R is an algebra in n manifolds with respect to disjoint union, just by taking products with M. I don't change the fact. I can just take this embedding right here and take a product with M. And products distribute over disjoint union. So this M0 times R becomes an algebra. And when I apply F to it, since F was symmetric monoidal, I again have an algebra. So now it makes sense to tensor over an algebra. And by similar reasoning that you used right here, that the half open interval was a module, when I cut each of these pieces are similarly modules over M0 times R. So similarly, there are embeddings. If my picture here looks as follows, here is my entire manifold M. I'm going to think of this decomposition as being given by a function, let's say, down to -1 and 1. And I'll think, this function will secretly be there because any decomposition you should always think of as being given by a Morse function, but you don't have to. And so let's say M plus 1 is the complement of this half open interval. So, well, maybe I'll draw it bigger here. This goes out to here. This goes out to here, and here's my one-dimensional trivialization of a tubular neighborhood. Sitting inside here is M0. This bigger part is M minus 1. This bigger part is M plus 1. And I've glued these two intersections along a thickening of M0. So I have maps. So M plus 1 is an R, M0 times R module, exactly because I have these maps, M0 times R, disjoint union, M plus 1, embedding into M plus 1. And this again works by retracting M plus 1 into itself a little bit, moving it in, and then with the extra space I've created, mapping a shrinking version of M0 times R into the complement that you've just, in the extra room that you've just made for yourself. Okay, so that a rough explanation right there is why this symbol makes sense. So so what is C going to be? I guess I should at least give you some indication of what sorts of properties C should have. So C here should be, so definition continued. So C should be a symmetric monoidal category, and this category should have some kind of homotopy theory. So you can just choose whichever one you like. It could be an infinity category. It could be a DG category, which probably most of you prefer. It could be a simplicial model category. Maybe it could even be a derivateur if I knew what that was. All right, so you got options, but it should have one of these properties, and sort of squirreled away in my definition somewhere, it'll have the property that C has something that stands in for quasi-isomorphisms, or homotopy equivalences. And if you're thinking of C as chain complexes, and it's fine just to think of C to be chain complexes from here on out, it'll have the property that isotopy equivalences go to homotopy equivalence, or go to quasi-isomorphisms. All right, so this is the definition here. And now, for the rest of the time today, I'm going to talk about this definition, or going to talk more about what this actually amounts to. So before I do that, I'd like to give a little bit of attribution here. I visualized using this board this way ahead of time, but when I visualized it, I thought I was going to have more space here. So I'm going to give some attributions now, and I'm going to have to write it small, and I mean no offense. So this definition is slightly different than Jacob-Lurie's formulation, but this is after a definition of Jacob-Lurie, which he calls topological chiral homology. And this definition had, I would say, two sort of main groups of antecedents, sort of conceptually. First being the sort of in conformal field theory, being the factorization algebras of Bellinson and Drinfeld. Which, I would say, sort of Siegel's idea on the algebraic formulation of conformal field theory. Sort of one group of antecedents. And the other sort of antecedent I would say is very different, coming from configuration spaces. And this comes from the sort of amalgamated or summable configuration spaces, which, similar to the configuration space models that were coming up in Ulrika's talk 45 minutes ago, and these that were formulated by Salvatore and Siegel. All right, so this is a definition I think is probably a little bit hard to get your mind around. And so it helps to do some examples. So I'm going to list out a bunch of examples now. And if you decide after I give these examples that you're bored and don't want to listen to anything else, you could just amuse yourself by trying to prove that these examples actually satisfy this axiomatic scheme. So the first example is the most basic, and also the reason why, which will become clear, I've made C be so general. I could let C just be chain complexes with direct sum. So I'm doing a weird here thing. I'm letting the tensor symbol, in this case, denote direct sum, but that's just the way it's got to be for this example. So in this case, an example of a factorization homology theory is we could now let, let's say, A now just be a chain complex. And then a factorization homology theory so would be just chains with coefficients in A. Let's say the functor M goes to chains on M with coefficients in A. So usual homology, usual singular homology. And then in this case, you might say, well, what is this thing right here? Well, when you put in the direct sum, what that becomes is just a usual formulation of excision. Namely, it's the slight refinement of what gives you, it's the short exact sequence of chain complexes that gives you the long exact sequence on homology groups. So another example, maybe again, where this is chain complexes with direct sum, is you could let A now be a chain complex with an action of, say, chains on the orthogonal group. And then you could take the factorization homology theory is the thing that assigns to a manifold M, let's say, cochains on M. Well, maybe I'll just say it this way. We can instead take a slight generalization where I take the twisted cohomology, where I twist this by the action of the orthogonal group right here. So there's a slight twisted version where I use the non-triviality of the tangent bundle to twist this homology theory by the action of the orthogonal group, and this you can check again satisfies these axioms. So it's and these, in the case of chain complexes with direct sum, these are the only things you get, just these two things. This of course being the example where the action is trivial. So perhaps hopefully it's reassuring that ordinary homology is an example of one of these factorization homology things. However, it's also a reason why I made C something more general, because otherwise the talk would be over, because I don't really have anything new to tell you about ordinary homology, certainly at this degree of generality. However, you might hope that you could get interesting other functors by sort of other homology theories by letting C be some other category, or at least some other monoidal, be equipped with some other monoidal structure. So that's what I'll do. So now, this next example, I'll now switch, or a series of examples. I'll now let C be chain complexes with a tensor product. So then, the following are factorization homology theories. Perhaps modulo some technical conditions. So the first would be the functor. Let's say that for given x a space, I could consider the functor M goes to the cohomology of the mapping space M to X, cochains on the mapping space. Now it's easy to see that if you take disjoint unions when you map out of them go to products, and then when you take cochains, products go to tensor products. So we see that at the very least it is indeed a symmetric monoidal functor, and then you can check that it actually satisfies these conditions right here, which boils down to a technical condition on X that ensures the convergence of a certain Eilenberg-Moore spectral sequence. All right, but anyhow, so here's one of the most basic examples to keep in mind about how these types of factorization homologies works. Or I could let X be a pointed space, which is, let's say, n connective. So the first n-1 homotopy groups vanish, the first n-1 homology groups vanish, and it's simply connected. And then another factorization homology theory is the functor that assigns to M chains rather than cochains on compactly supported maps from M to X. So I take all maps from M to X that outside of some compact subset go to the base point. So this had some chosen base point that's going to behave as 0 with respect to these maps, and outside of some compact subspace of M, it has to go to 0, the point. And so again, using the fact that this is n-connective, it's possible to verify that it satisfies these conditions. Maybe another example is now we could let G be a Lie algebra. This will look similar in flavor, and we could take the first functor to be the functor that assigns to M say the Lie algebra the Lie algebra homology of the compactly supported cohomology of M with coefficients in G. So you take cochains, compactly supported cochains on M with coefficients in G. This gets a Lie algebra structure, just the Lie algebra stockwise Lie algebra structure on G. And so that's a Lie algebra now. And now you can take it's a DG Lie algebra, and you can take its Lie algebra homology. And that, again, satisfies these axioms. This is a sort of compactly supported version, which I guess I should have put on this side, but there's also a non-compactly supported version where it's, I'll write it's as the Lie algebra cohomology of chains on M with coefficients in G. And maybe one last example. I could also consider the functor M, which just takes all the configuration spaces in M and takes a big direct sum over the configuration spaces in M. Maybe I'll let these be annihilated on the boundary. So I'll take a quotient of the subspace where at least one of the points lies in the boundary. Make this interesting. And take this, where V is some complex. Take a complex. I take the direct sum over I, the natural numbers, the non-negative integers, over the config chains on the configuration space, chains on the space, tensored over this, tensored with V, tensored to the I, and then take the diagonal quotient by the action of the symmetric group. So these are, I would say in some sense, these are the most basic examples of these kinds of factorization homology theories when you work in chain complexes with tensor product. If you're interested in trying to use these things to study manifold topology, these are not necessarily the most interesting, but they're the simplest to state, and in some sense the most interesting ones I think of as being deformations of these. So it makes sense to understand these thoroughly first. So now I'd like to formulate the following question. These, I've sort of, when you try to understand a homology theory, you want to understand it in terms of its local values. In other words, you'd like to kind of give the value on contractible spaces and then say that the homology theory is determined by its value on contractible spaces. Since basically they're all the same, contractible spaces up to homotopy, you say it's determined by its value on a single point. So you might ask, what's the analog here? What's the analog of just giving local values and then saying it's determined, by this kind of ramped up version of locality, or maybe I'll call this, just to give it a name, this sort of tensor version of excision, since when it's direct sum it reduces to usual excision. Sort of we could ask, how is factorization homology locally determined? Now, in usual homology, you don't have to really mess around too much with making a choice about what it means to be locally determined, because all contractible spaces are homotopy equivalent, and so you could just choose a point. But here we have two kind of local values, which I would say Rn and Dn. And so now it's not so clear which you should choose. So now you have a choice. So first, let's try Rn and just sort of see how it works, see what it would look like. So in usual homology theory, you have these functors defined on all spaces, and you just restrict to the value of a homology theory on a single point. And that's an equivalence, because taking singular chains gives you an inverse up to quasi-isomorphism. So here, we could take these functors from these symmetric monodal functors from n manifolds with boundary to C, and we can just evaluate, let's say on Rn. Well, there are really two variants of Rn, because there's Rn and there's the half open Rn minus 1 times 0, 1. I would say those are the two most basic open neighborhoods. So in other words, these are, Rn here stands for open neighborhoods, and this is a closed neighborhood. But the half open collar on Rn minus 1 is open in this category. It's an open submanifold of a manifold with boundary. So here, when you evaluate, you get some extra structure, this kind of algebraic structure I mentioned before, which I'll call a disk-n algebra with boundary. So this, just by definition, I'll say that it's a symmetric monoidal functor from this category of n disks with boundary to C. But I'll call these things algebras because they look a lot like algebras. So this is this looks a lot like the this is a sort of an equivariant or ribbon version of the Swiss cheese operad of Voronov. So you can restrict here, and you could try to identify. You could try to understand these functors in terms of just those two values and the extra algebraic structure they carry. Now, here,
Sorry. So the idea is it's a colored operad with.
That's, I would say, a more complicated way of saying this.
Sorry.
It's a symmetric monoidal functor. So if you prefer, if you like, you could say that it's an algebra over an operad with two colors. But I think it's simpler to say that it's a symmetric monoidal functor out of a category of manifolds and embeddings. But if you are, already geared up and ready to go in the lingua franca of colored operad theory, then yes.
Sorry, so your disks, your two colors of disks with a boundary and without a boundary?
It's Rn, and it's Rn minus 1 times the half open interval.
Oh,
Those are the two colors.
Okay, that's what you meant.
Okay, so there some of these disk-n algebras are particularly simple. Namely, let's say on just on Rn times 0, 1, it could just be the unit of the monoidal structure. So in particular, there's a functor here from disk-n algebras which are just augmented in C. So by disk-n, I'll just mean I throw away all these half-open intervals, and I'm just considering standard manifolds without boundary now. So now this
Rn minus 1 or plus 1?
right here, it's Rn minus 1 times 0, 1. Everything's an n manifold. Once, or eventually. So here I have a slightly simpler algebraic structure, and this corresponds to those functors, this collection of those functors from n manifolds with boundary to C, such that, well, if I take the value on some m, maybe n, where n is an n minus 1 manifold, times a half-open interval, that this is equivalent to the unit of C.
Is your arrow that way?
Pardon me? The arrow is this way.
The bottom,
These are,
the bottom arrow.
it goes from here to here. Special ones of these are given just by augmented algebras. So there's no reason that the value on this thing couldn't be something more complicated, but a particular simple one is just to let it be the unit. And so these correspond to just being an augmented algebra. So these, I would say, correspond more to our intuition from usual homology theory, because the homology of a half-open collar relative to its boundary, well, those things are homotopy equivalent since the collar just retracts onto its boundary. So you expect that to be 0, or the trivial thing. So it makes sense to kind of restrict to these things right here, which I'll do for the moment. So let me redraw this thing right here. So I'm interested in these symmetric monoidal functors from n manifolds with boundary to C, consisting of the collection of f, maybe I'll call these augmented, and these consist of those f such that f of an n minus 1 manifold times the half-open interval 0, 1 is the unit of C. Unit of the symmetric monoidal structure of C. Now, on this side, I can basically evaluate on Rn, and evaluate on Rn, and I get an augmented algebra in C. But I can also evaluate on the closed n disk, Dn, and here something a little bit interesting happens. here I get an n-disk co-algebra in C, which is co-augmented. So this is something that doesn't happen if I don't put in this augmentation condition, because what these structure maps are, in other words, if I have a bunch of embeddings, if I choose these illegal embeddings where the boundary doesn't go to the boundary, so I have a map right here which is not in this category that I've defined. If I choose one of these embeddings, boundary not going to boundary, boundary going into the interior, then I can define, for such a functor, I can define a wrong way map, which is extension by 0. Extension by 0, where this is now the single dn tensor.I. So because, why can you extend by 0? Well, I say 0, but I guess it's really extending by the unit. It's because we prescribe this fixed boundary condition, and we can define this exactly because we put the unit at the boundary. If we put anything else at the boundary, you wouldn't be able to define these maps. So I can speak a little bit more about the construction here, but I'm running a little bit short on time, so maybe I'll defer it to questions at the end if someone has a question about more about that. So now we have a very symmetric picture. Given one of these factorization homology theories with this boundary condition, you could think of the local values as being algebras, or you could think of the local values as being co-algebras. And the way I set it up, algebras seem preferred, but you could imagine that this being such a symmetric sort of construction that it's not clear which one you should think of as being, more basic. All right, so which one of these is better? How do you recapture the original, and what is the relation between them? Maybe will be a good motivating question for the next 8 or so minutes. So first, the question: how do you attempt to recover the values, say f of m, for a given one of these factorization homology theories from f of Rn or f of Gn, from this value together with its algebra structure, or that value together with its coalgebra structure. How can we do this? Well, there's a formal way of doing this. Whenever you restrict to some subcategory, there's this restriction, you can try to extend. So here, and there's only one kind of extension, since there's interesting maps from a bunch of disks into one disk, but not vice versa. So you can take the left count extension. So definition, the factorization homology, which I'll write with an integral symbol. The factorization homology, this is of m with coefficients in A, is, well, it's this co-limit, or really homotopy co-limit, over n disks embedded into M, well, I should say n disk with boundary embedded into M, where boundary goes to boundary, of the functor A as a functor on disks. So, or maybe I'll write it this way: for every bunch of copies of, well, okay. So this is one definition. This is the definition that Jacob Lurie first formulated. So that would be how you would attempt to recover the value from f of Rn. So that's the algebra. I guess I should say for an augmented n-disk algebra. And so then you can formulate the opposite definition for a coalgebra and say the factorization, let's say, to distinguish terminology, the factorization cohomology of M with coefficients in C, where this is an n-disk coalgebra, which I guess I should have said is a contravariant functor from the category of n disks to C. So I'll write this. I'll just move m up to the top of the integral sign rather than the bottom to distinguish. And this will be the homotopy limit over disk n with boundary over m. Sorry if that's hard to read. I guess there's no if. I'm sorry that it's hard to read. Disk n over m, but then you take the opposite category of C. So these are these sort of two formal ways of trying to extend back. This one wants to be the left adjoint of this functor, and the other one wants to be the right adjoint of this functor. And the way I formulated here, hopefully it looks pretty symmetric, and both seem like they should have a good chance of being a good idea.
Good chance of being what?
A good idea.
Oh.
I meant that in a non-technical sense. But I'm going to make it technical right now. So theorem. So I'm going to state now two theorems. Well, the first one will be immediate, and the second one will take me a minute. The first one is that this is a good idea, and this is a pretty good idea. So theorem. This is due to, this is something I proved with David Ayala and Hiro Tanaka. We proved this, I previously thought about this without boundary, and we proved a much more general version together where manifolds are allowed to have boundary or singularities or stratifications. So I'm stating the simplest version here. This first restriction is an equivalence. So it's an equivalence when you restrict to homology theories. So exactly these homology theories, manifold n with boundary in C, augmented, so satisfying this condition, this restriction in C is an equivalence. And the inverse is exactly given by this factorization homology construction. So this is an equivalence. Now the left-hand side is not quite an equivalence, but it wants to be an equivalence. It wants badly to be an equivalence. And if you perturb it just a little bit anyway, then it'll be an equivalence. So the right-hand side is an equivalence up to completion. And the relation between these two is something David and Ayala have been thinking about together, and that we call Poincare-Cazul duality, because it is simultaneously Cazul duality in the algebra setting and Poincare duality in the manifold setting. So the next theorem, I won't state this precisely because the technical conditions I think are not, well, you could ask about them later if you're curious about a more exact statement. And this is, in fact, not the most general version of the theorem that we proved because David doesn't like three different closely related theorems with three different proofs. He likes one general theorem with one proof. And so then that takes an extra year to write up. So this is with David Ayala, me too. So we call sort of an instance of a general result on Poincare-Cazul duality. So then for M compact, possibly with boundary, Then modulo some technical conditions. So say theorem, because I haven't told you exactly what the conditions are. Then if I start with A in augmented n-disk algebra, and let's say chain complexes, but it could be something else, then the factorization homology of M with coefficients in A is equivalent to the factorization cohomology of the Quizul dual of A. So this is of the interior, the Quizul dual of A, or M0 is the interior of M. And this dn right here, well, dn is the, and dn of A is the coalgebra structure discussed on this side of the board. So in other words, you take A right here, you take this factorization homology functor, and then you evaluate on dn to get a corresponding coalgebra, which is the factorization homology of dn. So maybe I'll write this more symmetrically. This I'll write as the factorization homology of Rn, and this I'll write as the factorization homology of Dn, the closed n-disk. And so then modulo some technical conditions, these two things are equivalent.
Is there a version of this when you have corners?
No. So yes. Yeah. 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 But that would be another year. You know? I don't know, you tell me, Ezra, can I get tenure if I do it with corners? So I, you know, I'll betray myself that I am the less general person in this partnership with David Ayala there, and you know, and maybe we've polarized each other. Okay, so why is this like why is this like Poincare duality? So to understand why it's like Poincare duality, let's consider the example. I stated this with chain complexes with tensor product, but it would also work in more generality. In particular, I could put in chain complexes with direct sum. So let's see what the statement becomes when I put it with chain complexes with direct sum. So now A is now, this algebra structure goes away. So A is just a chain complex. And let's say that it has a trivial action to make it as simple as possible for us. So I'm trying to understand the value now that I'm trying to understand. Well, this colimit, this factorization homology of M with coefficients in A, this is just, well, this is the colimit over all n disks over M of A, the homotopy colimit, and so this is equivalent to chains in M with coefficients in A due to excision. On the other hand, this factorization cohomology, coefficients in this coalgebra, when I take this coalgebra, this thing right here with A, this is just the n-fold suspension of A now. So what this becomes, this is a corresponding limit, and so what this becomes is the cohomology of M with coefficients in A suspended n times, with coefficients in that. And so now it's a statement that these two things are equal, which is exactly Poincare duality. These two things are equivalent. So I can take this shift and I can move it out there, and then that's the shifting in Poincare duality.
At what point do you have to pick an orientation of the manifold?
You know, I was hoping everyone was going to miss that, and then I could say, but I haven't used an orientation. But I guess it's wrong. So it seems like I may have proved Poincare duality for unoriented manifolds, which would be a problem. And in fact, this worried me when I first proved it. But then I realized, let me move this back in, that what's happened here is that this thing has a non-trivial action of the orthogonal group coming from this action of the orthogonal group on Dn preserving its boundary. So the right-hand side looks like its usual cohomology, but actually it's twisted by this action. And so this is the more general form of twisted Poincare duality. And so if M is oriented with respect to A, then you can untwist the right-hand side to get usual cohomology. And so maybe I'll just say that the proof here, which we're in the process of writing up, this is already on the archive and has been for a while. But let's just say that it's similar to the example. To this example right here, example circle. But similar, but it's kind of like a ramped up version where you use configuration spaces, norm maps, and a version of Alexander duality with local coefficients, something like that. Okay, so now I'd just like to go back and I'd like to reconsider those examples that I gave in the beginning. Those sort of bedrock, computations of factorization homology that I gave before, and then had the foresight to erase. So one of them, let me give just the one for, so let's say, so one of them, so I'll write it this way. It said that the factorization homology of Lie algebra cohomology of compactly supported cochains, now an Rn with coefficients in G, was equivalent to, I can dualize, I guess I'll write it this way. The factorization cohomology for, let's say, M, just for simplicity, I'll write closed here. The factorization cohomology, if you write it out, of the Lie algebra homology as a commutative algebra, modulo some technical conditions, which sort of up to duality, up to linear duality, this is the factorization homology of the Lie algebra cohomology of G regarded as a commutative algebra. So it's saying that these two things right here, this just looks like G shifted by minus n, and it actually, in characteristic 0, it has a trivial Lie algebra structure. So in fact, this object just looks like sim of G shifted by 1 minus n, using usual calculation of Lie algebra cohomology in the abelian Lie algebra. So it's saying that these two objects agree. So this object right here is, you could write this, it's a theorem that I proved with Dennis Gates-Gorey. This is a version of the enveloping algebra of a Lie algebra. So in the case n equals 1, this is the usual enveloping algebra of a Lie algebra. And so this statement becomes, well, there are not too many interesting examples of closed one manifolds. So it now becomes that up to duality, the factorization homology of the circle with coefficients in the enveloping algebra of a Lie algebra is equivalent to the factorization homology up to duality of Lie algebra cohomology. Now, using this excision result that I stated at the beginning, it's easy to prove just by cutting the circle along two hemispheres that the factorization homology of a circle for an associative algebra is Hochschild cohomology. It's equivalent to Hochschild cochains of U of G. So we're saying that up to duality and some technical conditions, Hochschild cochains on the enveloping algebra of a Lie algebra is equivalent to Hochschild homology is equivalent to that of Lie algebra cohomology. So I did not know this result before I thought through this much more general setting, but when I came across this, I realized that this can't be a fact that escaped algebraists all this time. So I believe that this equivalence, at least I found it for topological cyclic homology in the 80s in a paper of Feigen and Sigan. So if someone knows a different reference for it, I would be very interested so I could properly attribute it. But I believe that this, at least for cyclic homology, is sort of where this idea first dates to. Okay, so maybe I'll stop there and give Ezra time for questions. Yes.
Are there any questions or comments?
I had two questions already, but this I was just about to ask. This is something about causal dual
Right, yeah.
algebras.
So now I'm embarrassed because I had planned so clearly how I was going to work this in, but I fell behind on time, and now it's going to seem weird. So this construction right here that I again had the foresight to erase, this construction that looks quite symmetric in these n manifolds, and that I have these ways of going from n-disk algebras to n-disk coalgebras, which are augmented. So this is a direct, very geometric construction. You can directly construct this by these extension by zero maps on the closed n-disk. And so this is a statement about, this is really a statement about Cazul duality. And so what I had planned to advertise this, because I would say it's a very direct and elegant geometric construction of this functor from going from here to here, which was the fact that such a functor should exist dates to the early 90s in a paper of Getzler and Jones. And I would say it was to me just a really wonderful insight that if you take the EN operad, or these n disks, these are sort of equivariant versions of the EN operad because you have orthogonal groups acting, that these things that you should be able to take, let's say, the indecomposables, the EN indecomposables, and that should come with a shifted version of a coalgebra structure, again for EN. They proved at the level of homology, and there's been a cottage industry of trying to improve their homology level calculation to the level of chain complexes, which was achieved by Benoit Fresse, and to the level of spectra, which lots of people have worked on, and I don't know the exact status of, but it's really hard compared to how easy this construction right here is, which I believe you could work backward from to show that EN is Cazul self-dual as an operad. But this is a very clear geometric construction of this, and just sort of an implementation of this, in my opinion, really great idea of theirs in the 90s.
Go first. So on the left, the integral, the end, this integral sign, what's it called again? Factorization homology?
Don't mind me.
Does it have a name?
So the left-hand side I called factorization homology, and the right-hand side, the one for the coalgebra, I called factorization cohomology because it worked that way over here.
I'm very confused because if I put
M was compact. Compact.
Oh, M has to be compact.
Compact.
Oh.
That's why it's underlined.
Because I was seeing a... Yeah, that's true.
It's false when it's not
It
compact.
looks false because there's an orthogonal
It is
group
false.
in the way.
It's false. Compact.
Okay. Yeah.
So your factorization homology theory is a covariant functor. How is this related to what would happen if we were looking at a contravariant functor, something like a stack?
So I'm going to do this really great thing I learned from Roman Bezrukovnikov. I'm going to answer a different question. So this looks covariant, but this relationship between algebras and coalgebras it looks a little bit asymmetric. So you could ask for a formulation of this top thing, which is more symmetric. And so this is what this thing that David Isla came up with, which could well be known before, but we call this manifolds with a cone point. And so what happens, these are manifolds. This receives a functor from manifolds with boundary by sending a manifold to M quotient the boundary, which is adding a disjoint base point if there's no boundary. And so these these maps from M to N, these possibly cone-pointed singularities, are embeddings if you look at the complement of the inverse image of the cone point. So these are F such that F restricted to F inverse of N minus the cone point is an embedding. And so here, this is a more symmetric category. Namely, it includes disk N just by adding a disjoint base point, but it also includes disk N op by one-point compactification. So it has a subcategories both disk N and disk N op. And so this is the more symmetric version that I was talking about before. And so each of these augmented homology theories actually define a functor on these cone-pointed manifolds, which I think, I really like this construction. It's very simple and probably previously thought of, but I don't know an attribution. Okay.
That doesn't look anything like my question.
I can ask John whether Reg is allowed to ask another question.
Am I allowed to ask another question?
Can I refine my question? So I want to know, how is a factorization homology related to the thing which is also determined by local data that's called a sheaf or a stack?
So these are not sheaves on M.
Yeah, they're
because sheaves, they're not co-sheaves on M either. You can ask for some geometric object which they are co-sheaves on, and that's called the Rand space, introduced by Belenson and Drinfeld for this purpose, although it was previously studied by Borsuk and Ulam back in like the 30s. They called it the symmetric powers, which is not what we call a symmetric power. And then they made a mistake, and 10 years later, something bot corrected their mistake. They said that some subspace of S1 was actually, like 3 points in S1 was actually S3 to allow collisions. And then it went unstudied for another 40 years, or almost, and now it pops up here. So it is a sheaf. These things do form sheaves or co-sheaves on that space, and that sort of gives you a great geometric handle on understanding them.
More questions?
One last question.
Yeah.
Is there any way to put differential cohomology into this language?
I don't know.
Very good, very good. Anyone else want to get involved in this? Okay, well, thanks again to John for a great talk.